Okay, last time we talked about some pretty key and core stuff for kinetics, so let's review it just a little bit. It's good to review every once in a while. We started talking about mechanisms. That's this major section of the subsection of the section on kinetics. And we saw that one of the core ideas behind a mechanism is that not all reactions are equal. Some of them are elementary, some of them are not. An elementary reaction is something really simple like this that can take place in one step with no intermediates, no hidden species, chemical species around. And we saw that a whole bunch of things about these elementary reactions. You can write their rate equations, they're irreversible, they only go one way. What else? Each of them has their own rate constant, so a forward elementary reaction has a different rate constant than the same reaction but going backwards. You can write the rate law by inspection. There's really only two types of rate laws that apply. So yeah, well, maybe I should say something about that. I didn't say this last time, but this is a second order rate law, but there's another kind of second order rate law, which is one like this, right? One with two different species and overall second order power. And we used that later when we were talking about writing rate equations for mechanisms, but I didn't write it down here, so let me write it down now and fill that little lacuna. Anyway, all right, so, and then there's very rare third order ones. And then we started talking about mechanisms, the idea that something like this, a pretty common chemical reaction, isn't elementary because what's really going on is a whole bunch of bond breaking and bond reforming events, and those don't all happen in one step. Instead, you can write some series of simpler steps, elementary reaction steps, that overall accomplishes all the changes that have to take place for this chemical reaction to happen. And we saw the laws for how to write down rate equations from those mechanisms, and that's kind of the most complicated thing we did last time. We talked about how you write a rate equation, for example, here in this case for the species H2. There's one rate equation for each of the chemical species that's involved in the mechanism. And then we talked about how to do that for each of the species in question, what all the rules for that are. And in the end wrote down all the rate equations, so here's 4 of them. And here's a 5th one, and here's the 6th one up here. There's 6 species in this mechanism, and therefore 6 rate equations. And you can write them all down by inspection, basically, by looking at the mechanism and seeing how each species is created or destroyed by each of the steps, each of the elementary reactions that's in the mechanism. All right, so that's where we are. Now we want to take those ideas, that idea of a mechanism, and start exploring what kinds of behavior those kinds of things predict. And to do that, we could try to take some complicated thing like this one, but we wouldn't learn much from that. It's too complicated to understand nicely. So what we want to do is take some very simple cases. So this section is called Simple Mechanisms. We'll talk mostly about 2 different simple mechanisms, and then ultimately a third. And between those 3 simple mechanisms, understanding them reasonably well, we can get a pretty good idea for how all even more complicated things behave. So the first simple mechanism we're going to look at is I call reversible first order mechanism. We can write it this way. This is the way you'll see it probably most often in textbooks and in the literature. But notice this is a reaction that's reversible, right? So it goes, A goes to B in the forward direction, and B goes back to A in the backward direction. That means that's 2 elementary steps. So a somewhat more proper or rigorous way to write the same mechanism is down here as 2 distinct elementary reactions. A goes to B with rate constant K1, and then B goes to A with rate constant K minus 1. It's a convention that if you have a forward reaction and it's, let's say, the second step in some larger scheme, you call that K2, and then the backward reaction, the reverse reaction for that same thing, you call K minus 2. And so Kn and K minus n for some arbitrary one. So there's only one forward reaction in this case, so it's K1 and K minus 1. All right. Using the laws and tricks that we learned last time for writing rate equations, we can write down the rate equation for A right away. So dA dt is equal to minus Ka from this elementary step plus K1b from this, K minus 1b, sorry, from this elementary step. And then we can also do the same thing for B. So K1a for this elementary step and K minus 1b minus K1 minus 1b from this elementary step. And if you look, and so that's our two rate equations for our two species. There's only two species in this mechanism. If you look at that, you'll notice that this rate equation expression is just the negative of this rate equation expression. Multiply this guy by a minus sign and you get this guy, which means that dB dt is equal to minus dA dt. And we're going to exploit that fact a little bit further down when we actually go to solve these equations. But before we actually do that, before we actually solve, there is a very important result we can get. Well, first of all, both of these equations are not independent of each other. If this guy and this guy are just related by a minus sign, then only one of these is an independent differential equation that we can solve. So everything we can learn, we're going to learn from just one of these. We don't need to look at the second one. And that's generally true. When you write these things, all these rate equations down, very often they're not all independent. There's a set of 6 for the water reaction up above, but not all those 6 are independent. And here there's only 2, but only one of them is independent. So let's look at the one. Let's look at this dA dt one. And if we set that equal to 0, we are thinking about what happens when the reaction goes to equilibrium. So if I allow this reaction to go to equilibrium, I know that the rate of change for every chemical species has to drop to 0. So to investigate that, we set this rate equation equal to 0. That means this stuff over here is equal to 0 if these concentrations for A and B are at their equilibrium values. So this is AEQ and this is BEQ. If that's true, then we can rearrange that a little bit and we get that the concentration of B at equilibrium divided by the concentration of A at equilibrium is equal to the rate constant in the forward direction divided by, oops, that should have a minus sign on it, the rate constant in the reverse direction. So that's nice, but the important thing about it, the most important thing about it is notice that the reaction quotient from thermodynamics is also equal to, in this case, if we take the activities to be in molar units as usual, would be equal to the ratio of the B concentration divided by the A concentration. And if we're at equilibrium, then those will be the equilibrium concentrations. And according to everything we learned from thermodynamics, that should be equal to the equilibrium constant. And so we have a relationship between the kinetics and the thermodynamics. It's hard to overstate how important this very simple relationship is. It says that the equilibrium constant for an elementary reaction that goes both in the forward direction and in the reverse direction, so two elementary reactions really, one forward, one reverse, but for the same reaction. If you take the ratio of their forward to reverse rate constants, you get the equilibrium constant. That's an example of something called detailed balance. It's at the core of much of statistical, non-equilibrium statistical mechanics. There's a whole branch of literature, a huge branch of literature that's devoted basically to this relationship and generalizations of this relationship. So let me tell you, these things turn into matrices and it gets you got a lot of them and not just one and so on, but this is the core of it. This is the core idea. And so we'll use this relationship. It's widely used in the chemical literature. You'll see it everywhere. And yes, it shows also an important thing, which is that this kinetic relationship, this rate equation that we wrote up here, is consistent with everything we learned from thermodynamics. It's going to predict the equilibrium concentrations at the end of all. If we wait long enough in time, wait for everything to settle down to equilibrium, the kinetics will predict the equilibrium state of the system. The equilibrium state is buried inside of the kinetic equations in some not always obvious way, and this is one of the reflections or results of that fact. All right. So yes, it's a connection to thermo. If the equilibrium constant is e to the minus delta g over RT, then delta G0 is minus RT log K, which can be written as minus RT log of the ratio of the rate constants. So rate constant kinetic quantities over here, obvious thermodynamic quantity over here, it's obviously connection between thermo and kinetics. Notice also that it says that if, or this ratio, this relationship here says that if K1 is big and K1 is small, then this ratio, K1 over K minus 1, will be big, will be bigger than 1. That means the equilibrium constant will be greater than 1. That means the standard state delta G will be less than 0, which means you have a product-favored reaction. What that's saying is that if the forward reaction is faster than the backward reaction, then you're going to get more B at equilibrium, right? Because B over A at equilibrium is equal to K, which is equal to K1 over K minus 1. So if the forward reaction is fast, you're going to get more B when things settle down than you do get A. You're going to basically lose most of your A and create mostly B. And so the reaction is product favored as usual. All right, then if the reverse is true, if K minus 1 is, K1 is small and K minus 1 is big, then the ratio will be less than 1, the equilibrium constant will be less than 1, the delta G standard state will be greater than 0, and the reaction will be reactant favored, which means that if the forward reaction is slow and the back reaction is fast, then depending on how you started out, anyway, at the end, at equilibrium, you're going to end up with a lot of A and not very much B. All that makes intuitive sense, I think. Yes, this is just saying some of the things I was saying before, and that is that this is the sort of ground, most basic example of this principle of detailed balance. Let me say a little bit more about it. If you have some complicated kinetic scheme like this one, so a whole bunch of reactions that are all hooked to each other, the product of this first one creates is a reactant to the next one, and the product of that is the reactant for the next one, and so on. So all these reactions chain together in some big thing. It looks like a metabolic pathway in biology, and in fact metabolic pathways are like this. I have a picture of one down below. I guess it's too far down to find right now. But anyway, yes, if you've got some complicated thing like this, which does happen all the time in biochemistry and biology, then what detailed balance says is that if you consider any one of these reactions, any pair in this reaction, in this whole reaction scheme, like this one here with just A and B, then at equilibrium, detailed balance says that the equilibrium constant for just this part of the whole mechanism is equal to the rate constants for the forward over the reverse for just this part of the mechanism. And the same thing is true for this pair. There's another equilibrium constant for just this orange reaction, and it will be given by the ratio of the rate constants. And likewise for all of them, including, for example, this green one over here, which says that the equilibrium constant K5 is equal to the ratio of the rate constants K5 and K minus 5, and so on. So right away you can start to see that this principle up here has a lot of applications and can be used to say a lot of things that aren't immediately obvious, and is therefore quite powerful in a whole lot of settings. Anytime you've got a fairly complicated chemical system going on, then detailed balance becomes very useful, very powerful. There is a related idea that we won't talk about hardly at all in this class, but I'll mention in passing as we're going along, going through all this stuff, and that's an idea called microscopic reversibility. Microscopic reversibility just means that all real reactions are reversible. So an elementary reaction, remember, A goes to B, is taken to be irreversible. The reaction can go forward, you can turn A into B, but you can't turn B back into A. It's an irreversible step, and that doesn't sound very physically reasonable, right? It's fine as a rule from a mathematical point of view, but it doesn't sound like the way real molecules behave. If you can get a B from an A, then you ought to be able to get A back again by some set of manipulations. It might not be easy to do, but it should be possible in principle, right? All the atoms that were present in A are still present in B. All you got to do is rearrange the bonds to get back to A. There should be some way to do that. And there always is. That's what the microscopic reversibility idea says, that all real reactions have a forward step and a backward step. There are none that don't also have the backward step. The backward step is as always a separate elementary reaction, but it isn't missing altogether. It does exist. And so if you have, for example, a case like this, where the forward reaction is very fast, the backward reaction is very slow, that means the equilibrium constant for the reaction will be big, right? Because K1 is big, K minus 1 is small. If K1 minus 1, this back reaction, starts getting very, 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 very slow, then very often people will just ignore the back reaction. They say, well, okay, it's so product favored that that you just don't have any A left over at the end. We can pretend, at least for the sake of practical things, that it turns all into B, and in that sense, this reaction would behave to a good approximation as if it were irreversible. But microscopic reversibility says that there is no such thing as a truly irreversible reaction. All reactions are reversible, but they may behave as if they were irreversible in a lot of ways. And likewise, going back the other way, if the forward reaction is very slow and the back reaction is very fast and the equilibrium constant is very small, then it will look like an almost irreversible reaction going backwards, even though it's truly a reversible reaction. All right. Yes, if you have something, you can tell when something's effectively irreversible by looking at the equilibrium constant or by looking at the standard Gibbs free energy. And so if the standard Gibbs free energy is very large in either direction, if it's large and negative, then the equilibrium constant will be much, much greater than 1. The forward rate constant will be much, much greater than the reverse rate constant, and it will look like a forward irreversible reaction. If delta G is large and positive, then everything is reversed. The equilibrium constant is very small. The K1 will be much smaller than K minus 1, and it will look like it's effectively irreversible in the backward direction. Here's an example of that. Let's suppose we have this reaction, H2 plus Cl2 goes to 2HCl. I think that's an elementary reaction in both directions. Then the delta G for that reaction is minus 190.6 kilojoules per mole from the tables. And that gives you an equilibrium constant K at 300 Kelvin of 1.5 times 10 to the 33. So it's a great big equilibrium constant. There are bigger ones, but that's a big one. And that means that the forward rate constant will be 10 to the 33rd times bigger than the backward rate constant. So you can see why things behave in cases like this as if it were irreversible. That means this forward rate constant is 10 to the 33rd versus, the backward rate constant, which is 1. That backward rate constant is pretty tiny, pretty negligible compared to the forward rate constant. All right. That is all sort of the stuff that follows, or that's some of the implications that follow just from the very first look at this rate equation up here that we wrote down a while back. I'm coming back to it now. So we haven't even tried to solve this as a differential equation yet. We've just set this equal to 0 and worked out all the implications, and you can see there have been a lot of implications, basically. That's where the connection to thermodynamics comes in. But now that we've done that, let's talk about actually solving this differential equation. As above, there is a differential equation for B as well, a rate equation for B, but that's equal to minus the rate equation for A, and so we treat them as basically the same thing. We also, though, have this condition, right? Here, this equation, this differential equation has two unknowns in it. It's got A and B, so we've only got one equation and two unknowns. If we want to make this into a closed equation that we can actually solve, we need another equation. And here's what that equation is. It's the fact that if I have a certain amount of A and B to start with, so at time 0, that little 0 means these are the concentrations at time 0, then all you're ever doing is trading A's for B's and B's for A's, so that total amount of concentration for both species together can't change. It's got to be true that the concentration of A plus the concentration of B is equal to the initial concentrations of both of them together at all times, is a constant. And given that, you can see that if you take the derivative of both sides here, you can see that that's going to give us the fact that the time rate of change for A is equal to the minus the time rate of change for B. But it also allows us to eliminate B from our differential equation up here. We can write that B is equal to A0 plus B0 minus A, and then we can substitute in, and now we have a differential equation that just has A as a variable. And so now it's a closed equation that we can solve. Now, I've also, in the course of doing this, I've set the initial amount of B equal to 0. That isn't necessary, but it makes things very much easier, and I want to keep things as simple as we can at this point. So you can consider situations where you're sort of starting in the middle of the reaction and there's already some B present when you start, but I'm going to say that's not the case. I'm going to say we're starting with only A at time t equals 0, and in that case, this is our differential equation to solve. We could go through it all. There's nothing in this differential equation that's beyond the levels of calculus that everybody here in this class has, but it's a mess. It takes some time. We have only so much time in the semester, so I won't go through it. It isn't that hard. If you want to give it a try for yourself, I encourage people to. But here's the answer. Looks medium complicated. We're going to get more complicated cases than this in a little bit, but it's complicated enough. Here's the concentration of A. Here's the concentration of B as a function of time, right? So this is giving us the whole time course of the chemical reaction for this simplest of all reversible chemical reactions. It's going to tell us what the concentration of A is at every point in time, and also what the concentration of B is at every point in time, depending on the rate constants for the forward and backward reactions and the initial amount of A that was present. Let's look then at these relationships and see if we can make some sense out of them. I think it's valuable. I mean, we've solved the differential equation. We have these expressions. They, in principle, tell us everything, but you got to play with them for a little bit in order to see what they mean or what they're telling us. So let's consider some cases. Let's, for example, choose the forward rate constant to be 2, and the backward, that should be K minus 1. The backward rate constant to be 1. I don't know where that minus 1 came from. I was late last night, I guess. And therefore, the ratio of those two, which is the equilibrium constant, is 2. So an equilibrium constant of 2, that's pretty small, right? It's still product favored. It's not less than 1, but it isn't much bigger than 1 either. And so it's a slightly product favored reaction. If we look at our equations and we allow the time to get really big, so we're going to start taking this t out as big as we like. We're going to take the limit as t goes to infinity. Then this whole term in the expression goes away. for A goes away, this whole term in the expression for B goes away. And you can see that when that happens, we get that the concentration of A at equilibrium is equal to K minus 1 over the sum of the two rate constants times the initial amount of A that we had. And likewise, the B concentration at equilibrium is equal to K1. Notice K minus 1 over here, K1 here, divided by the sum of the two rate constants times the initial amount of A0 present. If K1 is equal to 2 and K minus 1 is equal to 1, then this thing in front here is just 1/3, and this thing in front is just 2/3, and so for this particular case, the equilibrium concentration is 1/3 times the initial amount of A, and 2/3 for B times the initial amount of A. And so if we plot those, here's what we get. We get, first of all, since we started with nothing but A, the A concentration has to go down, right? We're going to get some B created that's going to cause A to disappear. And so the A concentration falls steadily with time, but as time gets longer and longer, it's got to approach this final asymptotic value, this equilibrium value for A, which is going to be 1/3 of the initial amount that we started with, A0. And likewise, we started with no B, so that's going to rise, and we're eventually going to asymptote out at an equilibrium concentration of 2/3 of A. So behavior is pretty simple, and you can see that just by looking at the equilibrium values, by looking at the limit as t goes to infinity, and at least in this special case, we get a pretty good idea of what this whole graph looks like, right? We know it has to fall. It's going to, in fact, fall exponentially. You can see that in these formulas. And the B part has to rise, and it's going to rise exponentially. And we know how it has to limit out because we know what the values are at the far side of the graph here. Yes, it is worth noting, now that we have these formulas for what the equilibrium values of A and B are, that they are consistent with and satisfy the thermodynamic condition, right? The thermodynamic condition is that at equilibrium, the B concentration over the A concentration has to equal the equilibrium constant. If I take these formulas here, independent of any values that I plug in for K1 or K minus 1, and just do a little bit of algebra, I get that this ratio is equal to K1 over K minus 1 as it should be, and that is equal to the equilibrium constant. So again, in this special, more specific and concrete case, we see that the thermodynamics is buried or contained inside of the kinetics. And it takes maybe a little bit of work and a little bit of analysis to see that, but it is in there. And I will make a blanket statement that it's always in there. The thermodynamics is always contained inside the kinetics. It's not always easy to get out, but it is in there, if you set it up right. If you start getting some things that are crazy from a thermodynamic point of view, you did something wrong somewhere in there. All right, now let's consider another case. Let's consider the case where K1 is 10, so bigger. K minus 1 is 1, so now the equilibrium constant's a bit bigger. It's still not huge, but it's bigger than 2. It's now 10. In that case, the equilibrium concentration for A is, if I plug in for K1 and K minus 1 here, it's 1 over 11. And the B equilibrium concentration is 10 over 11. And so we get the same sort of behavior that we got before, except that we've got more B at the end and less A at the end because the equilibrium constant's bigger, right? It's a more product-favored reaction, and therefore we have more B at the end than we did before. And finally, let's take the third case, the opposite case. Let's suppose K1 is 1 and K minus 1 is 10. Now the equilibrium constant is only 1/10, right? The ratio of these two guys is only 1/10. So this is a reactant-favored reaction. And the equilibrium constant is less than 1. The delta G0 will be greater than 1. And if we plug into our formulas up here for the equilibrium constant of the equilibrium concentrations, we get 10/11ths for A and 1/11th for B, which means that the graph looks like this. What that means is that you started with all A, right, and you did get a little bit of B at the end, but it's a reactant-favored reaction. It doesn't go very far forward before it reaches equilibrium, and that's what we're seeing in the graph. The A concentration does go down, but not very much, and the B concentration does go up, and it's no longer 0, but it doesn't go up very far. And of course, you can see from all of this that if I change this to 1,000 or something like that, we're just going to get more and more extreme cases, right? We're just going to get more and more B at the end and less A. And again, if I made this 1,000, I would get less and less B at the end and more A. You know, basically, I would hardly get any reaction at all since I started with all of A, and so on. So from these cases, you can kind of see the full range of what the possible behaviors are for this very simplest of all mechanisms. Another thing sort of an overall point to make is that the process we've gone through here of setting up the rate equations, looking at what happens when we set all the rates equal to 0, and therefore finding out about equilibrium behavior, and also then solving and looking at special cases when you plug in particular values for the rate constants. That's a standard thing to do, and a very common and typical kinds of thing to do when analyzing a mechanism, no matter how complicated. There is one other thing I wanted to say. Yes, I guess this is a bit of a technical point. Most of you will not encounter this thing, but I guess I should be, just to be rigorous and complete, I should say that up here, let's see, up here where I say that at equilibrium, I set all the rate equations equal to 0, that's true, but it turns out, remember, that there's such a thing as a steady state. It's a situation where nothing is changing in time, but you're not at equilibrium. It's possible with chemical, you know, in equilibrium thermodynamics, you can never even get the steady state. The equilibrium thermodynamics only deals with the equilibrium states. But in kinetics, you can get a steady state. Not with this simple model, but with more complicated models, it's possible to set up a system that has steady state solutions. And then just setting these derivatives equal to 0 isn't enough to guarantee that you're looking at the equilibrium state. You might be looking at a steady state solution. There's more than one solution to the whole set of differential equations. Again, this is something of a technical point, but for those of you who go into this field or something related, it's just a warning to watch out for that trickiness. All right. That is, let's stop and see how much time we've used so far, and if there is enough time, I'll come back, but if there isn't, then we'll stop here for today.